Welcome to our presentation. Our topic is optimizing error-bounded lossy compression for three-dimensional adaptive mesh refinement simulations. Let's start with the background of adaptive mesh refinement, AMR. The AMR-based application will change the mesh or spatial resolution based on the level of refinement needed by the simulation, and use final mesh in the more important region and coarser mesh in less important region. In that way, we can achieve the desired accuracy and increase the computational and storage savings. Clearly, the AMR data generated by the AMR application will be hierarchical data with different resolutions. Here is an example of the AMR. We can find out that the grid structure changes with the universe's evolution. The red boxes indicate different resolutions within one time step. We have one resolution for this time step, two different resolutions for the second time step, and three for the last one. AMR data can be classified as patch-based AMR data and tree-based AMR data. The main difference between them is that the patch-based AMR structure saves the data blocks that will be refined at next final level in the current coarser level redundantly, while the tree-based AMR organizes the grids on the tree leaves. There's no redundant data across different levels. However, the tree-based AMR data can be more complex to perform post-analysis and visualization. And in this work, we focus on the patch-based AMR. Note that the redundant coarse data in the patch-based AMR will not often be used in post-analysis. So we discard the redundant coarse data while doing the compression to improve the compression ratio. AMR can help us to save the storage costs, but even with the help of AMR, the size of data generated by scientific applications could still be very large. For example, one NIC simulation with two levels of AMR, 50/50 full resolution and half resolution can generate up to 1.8 TB data just for a single snapshot. A single simulation can easily dump more than 100 snapshots and generate tons of data. So we need data compression to further save time and space for users. Furthermore, the compute capability of supercomputing systems is developed much faster than its storage and bandwidth. We have a widening gap between the compute unit and storage bandwidth, or between the mean memory size and storage bandwidth. As shown in the last two columns, the gap between the storage bandwidth and the compute capability is getting bigger and bigger. There are two main categories for data compression: lossless compression and lossy compression. Compared to lossless compression, lossy compression offers much higher compression ratios by treating a little bit of accuracy. There are some existing image lossy compressors, such as JPEG, but they do not have a good performance on the scientific data or floating point data because they are designed for integer, the RGB. In recent years, there's a new generation of lossy compressors that are designed for scientific data developed. They can achieve better performance on the floating point data than the image lossy compressor. There are some typical lossy compressors with their characteristics. For example, SZ is prediction-based and has a nice compression ratio. ZFP is transform-based and has high throughput. And the T-thresh is based on high-order SVD and performs nicely in 3D compression, but it is relatively slow due to the high time complexity of the HLSVD. In this work, we chose SZ because of the relatively high ratio and throughput. The main challenge with AMR data compression is that the structure of AMR data is comprehensive. We will have multi-level data with different resolutions as mentioned. The data of each AMR level are often stored separately in 1D. For example, as shown here, 0 for high resolution and 1 for low resolution. When the AMR data are needed for post-analysis or visualization, users will typically convert the data from different levels to a uniform resolution. In this example, we'll upsample the data in the cross level and combine it with the data in the fine level. To compress them, a straightforward idea is we can compress the 1D data for each AMR level directly. However, we will lose lots of spatial information, which is important for data compression. To leverage the 2D, 3D compression on AMR data, a simple idea is to compress the different levels together by upsampling the cross levels. However, in that way, we need to handle actual redundant data due to the upsampling. As shown here, we must handle 9 actual data points for this AMR dataset with only 7 points. The overhead of redundant data will be bigger when there are more data in the cross level or upsample rate is higher, especially for 3D AMR data. No matter which method is used, we have the problem of either low locality or redundant data. ZMesh is an existing approach to compress AMR data. It is an alternative solution to the 1D baseline. The key for ZMesh is that it pre-processes the 1D data based on the coordinate of the original 2D layout to smooth the 1D data to benefit compression. In other words, ZMesh places adjacent points in the 2D layout closer in the 1D array. By smoothing the 1D data, ZMesh can help the compressor to better take use of the redundancy of the dataset. However, ZMesh still has some limitations. First is ZMesh cannot compress AMR data adaptively or apply different compression configurations for different levels. This is because ZMesh will mix the data from different levels into one array and compress them together. But different AMR levels will have different importance, especially from the perspective of post-analysis, and this could be explored when we are doing the compression. Also, ZMesh compress the AMR data in 1D, and it cannot leverage high-dimensional compression. In our work, we propose to adopt 3D compression for each AMR level separately. However, in that way, the data will be split into multiple levels, and each level will have many empty regions and irregular data distribution, as shown in this figure. Therefore, we propose 3 pre-processing strategies to mitigate the issue of irregular data distribution. We also propose an approach to select the best fit strategy based on the data density of each AMR level. This is the overview of our proposed TAC. It has a density filter that chooses the best pre-processed strategy for each AMR level before compression. I will now show our proposed 3 strategies one by one. First, a naive solution to handle the irregular 3D data is to fill the empty regions with zeros and pass a large 3D block to the compressor. However, when most of the regions in the data are empty, for example, 77% of the data is empty in this figure, we must fill many zeros, which will greatly increase the data size and affect the compression ratio. Therefore, we first propose to use a naive tensor representation called NAST to remove the empty regions, as shown here. We first partition the data into unit blocks, then we remove the empty blocks, linearize the rest 3D blocks, and pass the array to the compressor. However, to completely remove the empty regions, the unit block size needs to be relatively small compared to the data size. For example, we have 16 versus 512, resulting in lots of data on the boundary. And the boundary data has less spatial information compared to the non-boundary data and will affect compression performance. To address this problem, we further propose an optimized sparse tensor representation called OPST to remove the empty regions and maintain a larger subblock size. This is a 2D example for OPST. That is, we still partition the data into unit blocks. Blue means non-empty and white means empty. Then, for each unit block, we use dynamic programming to save the size of the max square whose bottom right corner is that unit block. For example, a 2 here means we can have a 2 by 2 block from bottom right to upper left. Then, we extract the subblock from the original data according to BS. For example, according to this value, the 2 by 2 subblock will be extracted. And since the data will be changed after the extraction, we need to partially update BS. After extracting all the subblocks, we put them into several 3D array based on their sizes and pass them to SC. Now, I will show a visual comparison of the compression error between NAST and OPST. Note that brighter means more error. As we can see, the OPST can significantly reduce the overall compression error. The OPST approach proposed for low-density data has a high overhead when the data is relatively dense. This is because OPST needs to update BS array each time we extract the subblock, and the update cost is highly related to the data density. The time complexity of OPST can be expressed as this. N is the unit block number and D is the data density. Note that density describes how dense the data is. For example, the density of 23% means that 77% of the data is empty. To address the high overhead issue of OPST, we propose an adaptive KD tree. It has lower time complexity. The AKD tree also removes empty regions and extracts subblocks. This is a simple 2D example. That is, we still partition data into unit blocks. Then we use a tree to represent the data. Each node is associated with a subblock of the data, and each node maintains the number of non-empty unit blocks within it. For example, for this node, we have 8 non-empty unit blocks, and for this node, we have 4. Then we will adaptively split each node from the middle among one of the dimensions. We will keep splitting until node is full or empty. After the construction of the tree, we will collect all the 4 leaf nodes and send them to the compressor. Note that if we keep splitting subblocks in a fixed way, for instance, let's say from X, Y, X, we'll get 2 2x2 subblocks for node N to 2. But the largest possible subblock could be 4x2, as shown here. Therefore, we will now present our adaptive splitting approach, which can select a dimension to unevenly distribute its non-empty unit blocks to its children to help us get bigger subblocks. We categorize the nodes into 3 different types: the cube, flat, slim, as shown here. Starting from the cube node D, we first divide it into 8 arc blocks. Then we can get the count of the non-empty unit blocks inside each arc blocks. After that, we can decide along which dimension to split based on these counts, as shown here. We compare these 3 values and choose the dimension with the max difference to split. Let's say we will split along the z-axis and get 2 fat nodes, D1, D2. Then for the final nodes such as D1, we can reuse these 4 counts to decide how to split. And finally, we just simply split the slim node D11 along the x-axis. And this process, flat, cube, flat, slim, cube, flat, slim, will be looked until the node is empty or full. We only count every 3 steps for the cube nodes. So we can load the time complexity of the AKD tree to 1/3 and log n. For high density data, as shown in this figure, there's not much room for us to remove empty regions. Also, due to the data partition, OPST and AKD tree will hurt the data locality. So we first propose to pad zeros into the few empty regions instead of removing them before compression. However, these padded zeros can significantly affect the prediction accuracy of SC, resulting in high compression error on the boundaries. To address this issue, we use ghost shell padding to diffuse boundary values to a padding layer. Here is the high-level idea. We still partition the data into unit blocks, then we will pad each empty unit block using the average of its non-empty neighbors' boundary data. Some empty unit blocks can have more than one non-empty neighbor, as shown such as here, and we will use the average value of all its neighbors for padding. As shown here, compared to the ZF approach, GSP can significantly reduce the compression error for the boundary data. Now we have 3 strategies for different densities, and we propose to use 2 data density thresholds to determine when to use which. To decide the first threshold between OPST and AKD tree, we perform a series of experiments and found out they have almost same compression performance in terms of bit rate and PSNR. Then we evaluate the time costs of the 2 methods. As shown in this figure, the time of AKD tree is relatively stable, while the time of OPST increases linearly with the data density. This is consistent with our previous design goal. AKD tree is designed to address the high time of overhead issue when the data is denser. Since they have a similar speed when the density is around 50, we choose T1 to be 50%. We also evaluate AKD tree and ghost shell padding, GSP on different datasets with different densities to determine the threshold T2 between them. As shown here, when the density is relatively low, the AKD tree, the gray curve, outperforms ghost shell GSP, the blue curve, in terms of bit rate and PSNR. Then GSP gradually outperforms the AKD tree when the data gets denser and denser. We can also observe that they have similar performance when the density is around 60. So we use T2 equals to 60% for choosing between AKD3 and GSP. Now I will present our experimental setup and evaluation result. We mainly focus on the RMX framework, particularly the NICS cosmology simulation. It's a state-of-the-art extreme-scale cosmology code. We use 7 datasets generated by 2 real-world runs with different number of AMR levels. The test platform is equipped with 2 28-core processors and 384 gigabit memory. We first evaluate the rate distortion of TAC and compare it with the baselines. For the 1D baseline, as shown here, the TAC, the pink curve, outperforms the 1D baseline across all the datasets. For the 3D baseline, blue curve, TAC has much better performance when the fineness level has a relatively low density, or the decompressed data has a high PSNR, as shown in these 3 figures. However, when the fineness level has a relatively high density, as shown in the bottom left figure, TAC cannot dominate the 3D baseline. This is because if the fineness level of an MR dataset has a high density, this dataset will be similar to a non-MR dataset with uniform resolution. So there's no need to use our TAC. Instead, we can directly use the 3D baseline that upsamples the coarse level data and compress the merged uniform data. Because when the fineness level is dense, the overhead of redundant coarse data will be small. Also, the 3D baseline that compress the whole dataset together can better leverage the spatial information than the level-wise compression, TAC. We can also find out that Z-mesh is slightly worse than the 1D baseline on our tested data. This is because we remove the redundant coarse data in the dataset before compression, while Z-mesh need to make use of the data redundancy between each MR level, and it cannot improve the smoothness if there's no redundancy in the AMR data. We also evaluate the overall throughput, including preprocessing, compression, and decompression. As shown in the table, compared to the 3D baseline, the throughput of TAC is up to 75 times higher on the round 2 datasets and 2.4 times higher on the round 1 datasets. This is because the round 2 datasets have low density in the fineness level, resulting in high overhead of redundant coarse data for the 3D baseline. Moreover, TAC is worse than the 1D baseline on the round 1 dataset because of the preprocessing overhead. Note that on the T3 and T4 datasets, our throughput drops due to a relatively heavy launching time compared to the overall short time on the small datasets. We then evaluate TAC with 2 pulse analysis, power spectrum, and halo finder to demo the benefit of the adaptive error bound method. In short, power spectrum describes how much structure exists at the different physical scales, and halo finder identifies over-density halos in the dark matter distribution. TAC can apply different error bounds to different MR levels based on the needed of pulse analysis, the upsampling rates of coarse levels, and the rate distortion trade-off between different MR levels. For power spectrum, we compare the power spectrum PK prime of decompressed data with the original PK and accept a maximum 1% relative error, the red dashed line, for all k less than 10. As we can see, under the same compression ratio, TAC with uniform error bound has a similar power spectrum error compared to the 3D baseline. And after adjusting the error bound for each MR level using the 3 steps, we can see that TAC with adaptive error bound can lower the power spectrum error and outperforms the 3D baseline. For halo finder, we evaluate the mass change and the sales number change for the biggest halo we identify. We can see that TAC with adaptive error bound produce the best halo finder quality. In conclusion, in this work, we propose an error-bounded lossy compression for 3D AMR data called TAC. In TAC, we propose to compress each AMR level separately in 3D, and we propose 3 pre-process strategies that can be adaptively chosen based on the density of each AMR level. We improve the compression ratio compared to the existing approach by up to 3.3 times under the same quality loss. With our level-wise compression approach, we can tune the error bound ratio of fine and coarse levels for better post-analysis quality. In future work, we will apply our approach to more AMR simulations. We will also address the issue of relatively low throughput on small AMR datasets. And that's it. Thank you for listening. All the questions and ideas are welcomed.